Okay, this is the lecture from Monday the 4th, but it's really a continuation. Okay? All right, this is the lecture from Monday the 4th, but I'm actually continuing and giving 2 lectures on Wednesday the 29th because I'll be out of town on the 4th. So that's why, for those of you watching the tape, that's why this stuff is on the board. No point erasing it and then writing it again. So basically, I'm continuing from where I left off 10 minutes ago. And where that is we have this interesting result here. And what we would like to do is we would like to be able to invert that. That result comes from here. So I'll start over here. And I'm going to make an argument by which I can actually get an explicit solution for B of t. That is like this, except not in terms of itself. So I'm going to do that by looking on the bottom of page 230. And I'm going to look at the MD1Q. So this is a special case where the service times are deterministic or constant. And I'm going to let Nj equal the number of customers served during a J busy period. But this is the J busy period now in MD1. And I'll define F sub n super J. This is just a notation. That's the probability that the number served during a J busy period is exactly little n. Now, it's easy to write an expression, a recurrence that we can solve for this as long as I have constant service times. Because you can see in a minute that what I'm going to write down is correct. Okay, I want to calculate the probability that during a J busy period, I serve exactly n customers. So obviously, n must be at least J. So let's take the case in which n is equal to J. If n equals J, what that means is that the busy period consists only of those customers that were originally there, and no other customers arrived during those service times. So in that case, that means that there are originally J customers present, and there must be no arrivals during those J service times. Now, each service time is of length tau, so that means that tau times J is the total length of the service times of those J customers. So the probability that there is no arrival during that time is e to the minus lambda tau J. So in other words, if my n, the number that I serve, is equal to the number that's originally there, that will happen if and only if during those J service times, which last exactly J times tau, there are no new arrivals. Okay, now how about the case in which n is greater than or equal to J plus 1? So now we say, okay, first of all, let's look at those original J customers. And let's say that exactly K customers arrive during those J service times. The probability of that is lambda tau J to the K over K factorial e to the minus lambda tau J. Need a little bit more room here. Okay, so this is the probability that during the first J service times, original ones that were there, exactly K new customers arrive. Now, if K new customers arrive, then the total number that's to be served must be K. So that means that during the remaining busy period, during the K busy period that these K arrivals generate, I must serve exactly n minus j customers. And that will be summed over all possible values of k from 1, because we already took care of the 0th case, to n minus j. Okay, so let me say that again. What's the probability that during a j busy period I serve exactly n customers? It's the probability that during the j service times of those original customers, exactly k new customers arrive, and then during the additional k busy period that those customers generate, I must serve altogether n minus j additional customers. Then I will have served altogether n, and I sum this over all possible values of the number of arrivals during the first j service times, as the index k runs from 1, because I've already taken care of the 0th case here, up to n minus j. Okay, so now I have a recurrence, and it turns out that this recurrence is easy to solve. In fact, let me write down what the answer is. It's easy to verify that this is in fact the answer. Fnj is equal to the following. It's equal to j over n times lambda tau n to the n minus j divided by n minus j factorial times e to the minus lambda tau n. And this is, of course, valid as long as n is at least j. Okay, now you could say, so what? I solved this problem, so now I have the explicit expression for the probability that during a j busy period, a total of exactly n customers are served. But look at the form of this thing. This is very strange looking, because what this says is, if I'm to serve exactly n customers, and I start out with j, that means that n minus j additional customers must have arrived during the busy period. Now, we know those customers are arriving according to a Poisson process. And we know that altogether there are going to be n of them. So that means this is the probability now, according to a Poisson process, that during a time which consists of n service times, n tau, if customers arrive according to a Poisson process with rate lambda, that exactly n minus j customers will arrive. So we know that if we start out with j and we ultimately serve n, then there must be exactly n minus j new arrivals. We know they must occur according to a Poisson process, and we know that the total length of the busy period, since it consists of n customers, must be n service times. Since we have constant service times, it must be a time n times tau. And then there's this piece right here. Now, this Poisson piece is rather strange, because this says that during this interval, which consists of n service times, I have exactly n minus j arrivals. But we know, for example, that there can't be any arrivals during the last service time. Because if there are, then it's not the last service time. That is, as the whatever customers are there, the server continues to work as long as there's work to be done. So during the last service time, nobody can arrive, because if someone does arrive, then the busy period will last longer than that. Furthermore, since we know that nobody arrives, that means that, well, let me skip that statement because I forgot that these service times are constant. Okay, so we know that during this interval of length n tau, we know we're going to have exactly n minus j arrivals according to a Poisson process, but we know that none of them are going to occur there. In fact, these n minus j arrivals must occur in such a way that during the times that they arrive, the server never goes idle. Because if those customers happen to arrive in certain kinds of bunches, then they're not going to arrive in such a way that the server will be continuously busy. In other words, they have to tend to arrive towards the front rather than the back. So this is the probability that we have exactly those arrivals. So this must be the conditional probability that those arrivals occur in such a way as to constitute a busy period. So what I did was I wrote some equations and I solved them, and this is the solution. And then I get this solution and I look and I see it has two pieces. And one piece is the Poisson piece and the other piece is something else. So that something else, that multiplying factor, must be the conditional probability that this number of arrivals occurs in such a way that they constitute a busy period. Now, that must be what this is. The question is, well, suppose that I didn't have constant service times, then what? Would this have the same interpretation? And the answer, it turns out, is yes. Okay, so that's amazing. And in fact, that whole idea was explored by Takash, who wrote a book entitled something like Combinatorial Methods in the Theory of Stochastic Processes. And he proved lots of theorems of this type in which he basically reduced stochastic processes to combinatorial problems. So the proofs of the statements I'm going to make are in his book, and his references given to that. But let's accept that as true for the moment now and use that as a working hypothesis to see whether we can get anything further out of it. Again, this is my strategy, my philosophy of doing queuing theory, which is you use whatever evidence you have, even if it's not mathematical evidence, even if it's not proved, and then you, if you get the results that you want, then you go backwards and try and justify them. Okay, so I'm going to now look at the ordinary MG1 busy period instead of MD1. And I'm going to argue by analogy and get an answer. Okay, so now I'm going to define something else, because if I know that I have MD1, then if I know how many customers are served, then I know exactly how long the busy period is. But in general, those things are related, but they're not deterministic. Okay, so now I'm going to write an expression for what I call B sub j of n and t. So I'm going to write down equation 873. Now what this is this is the probability, this is a distribution function for a j busy period that jointly the number of customers served is n and the total length of the busy period is less than or equal to t. If I had MD1, then of course, if I serve n customers, the length of the busy period is exactly n times tau. Okay, so now let me make this argument. And I'm going to argue by analogy with this statement right here. So first of all, I know that that if I'm going to serve n customers, then the total length of the busy period must be n service times. So h star n of x, the differential of that is the probability that the n service times last exactly x. Okay, star means convolution. So that's the probability that the n service times, because I'm serving n customers, lasts exactly x. Now, during those n service times, just like during these n service times, I must have n minus j new arrivals according to a Poisson process. That probability, if their sum of those service times is x, is lambda x to the n minus j over n minus j factorial times e to the minus lambda x. And now, x, of course, can be anything from 0 to t, because we want the sum of those n service times to be less than or equal to t. Okay, now what we have here, this piece, is exactly like this piece. And now we have the same problem. This is the probability that during the n service times that constitute the j busy period, I have exactly n minus j arrivals, so that the total number is n, and the total length of the busy period is less than or equal to t. But remember that these arrivals occurred according to a Poisson process just here, but I have to multiply that by the conditional probability that they occurred in such a way that during that interval the server never becomes idle. Because if it does, then it's not a busy period. In particular, I can't have anybody arriving during the last service time. Because if it's the last service time, nobody can arrive during it, or it wouldn't be the last service time. And not only that, but if the service times have are random variables, and we know that nobody arrived during one of them, then that would tend to make that service time shorter than the others. Because if I condition and tell you that I have a service time, and I tell you that nobody arrived, then it's probably a short time. If I told you that I had a lot of arrivals, then it's probably a long time. Okay, so I'm going to be bold and assume that that conditional probability is independent of the distribution of the service times and is exactly j over n. It turns out that that's true. That's what Taka showed. But I'm assuming it because that's the easiest thing. That's the nicest thing that could possibly happen. So you have to be an optimist here. You have to assume things and hope that it works out. Now, if that's true, then I can calculate the distribution function of the busy period by simply summing the distribution function of the j busy period over all values of n, the number served during that, as n runs from j to infinity. Okay, so from that, I simply get then that the distribution function of the j busy period is equal to the sum as n runs from j to infinity of j over n times the integral from 0 to t of lambda x to the n minus j over n minus j factorial e to the minus lambda x dh star n of x. In particular, suppose j equals 1. We actually got more than we needed. Suppose j is equal to 1. Then we get b of t. Well, let's see, I won't even bother to rewrite it. I'll simply erase the j here, so it's b of t, and make this j a 1. So this becomes a 1, that becomes a 1, that becomes a 1. That's b of t. All right, now it's an exercise, just like MG1Q kind of exercise from the viewpoint of arrivals, the same kind of stuff, to take transforms of this and show that you get this. If you can do that, which can be done, then what that proves is that this is in fact the inverse. So the strategy is, I considered the case of constant service times. I got an answer which is easy to get. Then I generalize that by making a leap of faith, a guess, that this factor remains the same. Then I specialize that to the case in which j is equal to 1 and got that. And then I took transforms of this and got this. And therefore, by the uniqueness of transforms, it must be true that this is the inverse of that. And it also must be true that my interpretation of j over n is correct. Yes?
The n is the power of the star, or?
No, this means n-fold convolution, not power.
N-fold.
Right. N-fold self-convolution. This means h star of n is the distribution function of the sum of n independent, identically distributed variables, each of which has distribution function h. So if my service times distribution function is h, then the differential of h star is the differential of the distribution function of the sum of n independent identical service times. Okay, so what this says is, that's an important point here. This is the probability that in a j busy period, I have exactly n customers served in total, and the total length of time it takes to serve them is less than t. And if I'm going to serve altogether n, then the total length of the busy period must be n service times. So this is the probability that those n service times add up to exactly x. And then this is the probability that during those n service times, whose length is x, exactly n minus j customers arrive according to a Poisson process. If n minus j arrive and I started out with j, then I will have served altogether n. And then if I add up as x varies from 0 to t, I have the total busy period less than or equal to t. But I still have to take into account the fact that these Poisson arrivals have to occur in such a way that they constitute a busy period. And as an example that that's not every possible way, I can't possibly have any arrivals during the last service time. Because if I did, it's not the last service time, the thing would continue. So the last service time in a busy period, in any busy period, there are the service times. It must have the property that nobody arrives during it. Which means, of course, that all the customers must have arrived prior to that. So we know that during this interval, exactly n minus j arrived according to a Poisson process, but we know that they didn't arrive uniformly spread out through that interval. We know that they tended to arrive at the beginning. They tended to arrive in such a way such that the server never became idle until here. And the question is, well, what's the probability of that? That sounds very complicated. But we already know that if the service times are constant, it must be this. So therefore, we're making the leap of faith and saying that, well, that probability doesn't depend on the distribution of the service times. Now, maybe it does, maybe it doesn't. But if it doesn't, then I'll use the same factor. Then carrying everything through, I see that if I then take the transform of this, I get what I know the transform must be. Now, there's a lot of work to go from here to here, but that's beside the point. If I take the transform of this, I get this, and therefore it must be true that this was the correct interpretation. Or even if it wasn't the correct interpretation, regardless, I could have made lots of mistakes that cancel each other out. All I know is that if the transform of this is this, then this is the inverse of that, and that's, by uniqueness of inverses, I'm done. Okay? So you see that the results that you're getting here, they're sort of different from the first part of the course. First part of the course, the emphasis was on calculating things that were directly useful in performance analysis. Now what you're doing is you're calculating things, or you're getting insights, and you're calculating things which is going to turn out are useful as pieces of analysis of more complicated systems, for which you will then get performance measures. Because for ordinary MG1, we already know how to calculate the utilization of the server, the distribution function of waiting times, the probability the server is busy, and so forth. But now with these insights, we're going to be able to do more, such as vacation models and polling models and other things. Okay on this? Okay, so now I want to extend this line of reasoning, or not extend it so much, just continue it. So I'm going to look at some of these exercises, starting on page 233. So first of all, let me look at exercise number 19, called the polite customer. So exercise 19, page 233. It says, let us call a customer polite if she declines to enter service whenever anyone else is waiting for service, and denote by W sub P her equilibrium waiting time. So clearly no queue is big enough for more than one polite customer at a time. So the polite customer comes in and says, okay, everybody go ahead of me, and I won't enter service until I'm the last person. Of course, if somebody arrives while I'm there, in this model, I keep the server, I don't get preempted. But nevertheless, while I'm waiting, if anybody else arrives behind me, I'll let them go in front of me. Now, that gives sort of a bound on waiting times, as long as they're non-preemptive for other Q disciplines, because it seems intuitively obvious, although you've got to be careful about intuition in this subject, but it seems intuitively obvious that in any Q discipline in which the customer, the test customer, does not let everybody else ahead of him, then for those Q disciplines, the waiting times must be less. So the worst waiting time you can have is if you decide to let everybody go in front of you. Okay, so this is a bound, and it's sort of interesting for its own sake, so let's see if we can analyze it. Okay, so let me do it over here. So part A says, argue that. We want to calculate the probability that the waiting time for the polite customer is less than or equal to x, given that it's positive. Because if the polite customer arrives and finds the server idle, then she enters immediately. Okay, so what is that going to be? And the question says, well, you don't really have to analyze it. You can write down the answer by inspection. Because what happens here? Okay, here is the busy period, like so. What happens to the polite customer? The polite customer arrives when the server is busy. Otherwise, she doesn't wait at all. So that means she arrives during a busy period. Now, how long does she wait? Well, she waits the remainder of the busy period, and then she enters service herself. Now, the busy period may continue after that if somebody arrives during her service time, but that's not the question. So therefore, the polite customer's waiting time is just the forward recurrence time of a busy period. So what's the answer? Well, it's 1 over the mean of the busy period, which we already calculated. We have a formula for that, times the integral from 0 to x of 1 minus b of t dt. Okay, so there you are. There's nothing to it now. Again, it's the forward recurrence time result. Now, you explicitly know what this is, although it's complicated, but that's not the point here. Because you're not usually interested in actually computing these things. You're interested in either you just like the way things fit together, or you're interested in using them as pieces to a bigger problem. All right, so this was equation 1. But of course, that's conditional. Suppose we want to get the unconditional, and then the answer is obvious. Well, what's the unconditional probability distribution function of the waiting times for the polite customer? Well, the probability that the polite customer waits less than or equal to x is, first of all, the probability that the polite customer doesn't wait at all, that when she arrives, she finds the server idle. And that probability, of course, is 1 minus rho. Okay, now, with probability rho, in fact, she finds the server busy. And in that case, her waiting time distribution function is exactly this. It's exactly the probability of waiting less than or equal to x, given the condition that when she arrives, she finds the server busy. So what you do is you replace this piece here by this. And you use the fact that B, as we've already proved, the mean of the busy period is equal to tau, the average service time, divided by 1 minus rho. So you plug this in here, you put this here, you combine with that rho, and you get the answer that's given in the book. Okay, then it says for part C, show that the expected value of the waiting time for the polite customer, given that the polite customer waits, is given by the following formula. And it gives a formula, but the way to do it is obvious because you just use the forward recurrence time result. And the forward recurrence time result is that this would be the average over 2 plus the variance of the busy period, I'll call it sigma squared sub b, divided by 2 times the mean, if I remember the formula correctly. And now, if I plug in for b, the result tau divided by 1 minus rho, then what I will get will be, after some arithmetic, if everything works out right, what I'll get is tau divided by 2 times 1 minus rho. Okay, that comes by plugging in for b right there, plus 1 minus rho sigma squared sub b divided by 2 tau. Okay, so now we have an explicit formula for the average length of time that the polite customer waits, and it's in terms of the utilization of the server, the average service time, and the variance of the busy period. But what's the variance of the busy period? Well, the variance of the busy period is easy to get. I don't think I'll work it out. I'll just show you how to do it. Remember that, well, let's see. We had this equation which said that the Laplace-Dirichlet transform of the distribution function of the busy period was the Laplace-Dirichlet transform of the distribution function of the service time evaluated at s plus lambda minus lambda beta of s, if I remember it correctly. Okay? And then I could calculate b, which was minus the derivative of beta evaluated at 0. And then I could evaluate the second moment. Let's see, what do I call it? Why don't I just call it B2, which is beta double prime of 0. And in fact, a short time ago, I had actually written down exactly what that was. That's obtained by differentiating implicitly through this twice and setting s equal to 0. And this, of course, is the second moment of the busy period distribution. So the variance of the busy period distribution is equal to the second moment, that is the expected value of the square of the random variable, minus the square of the expected value. So whatever that formula was, we know what it is, we know what this is, you plug this into here, and the end result is that you get the answer that's given in the book. At least I think you get the answer given in the book, which is the expected value of WP, given that it's not 0, turns out to be equal to tau squared plus sigma squared divided by 2 tau times 1 minus rho quantity squared, where this sigma squared is the variance of the service times. Okay? Any questions about this? So, and the arithmetic can get confusing or complicated, but the strategy, I think, is straightforward.
Yeah, tau squared is different from tau b squared.
Tau squared is the square of the average service time.
I mean, sigma squared. This one is different.
Sigma squared, this is the variance of the service times. This is the variance of the busy period. So to calculate the variance of the busy period, by differentiating through this, you get the variance of the busy period in terms of the parameters for the service times. And that's the objective here, because it's assumed that you know the service time distribution parameters, but you don't know necessarily the parameters of the random variables that are derived from the service times. Okay, so that's a polite customer, which is kind of interesting and which gives a bound on things. Here's another one, service in reverse order of arrival. This is exercise number 20 on page 234. Okay, so can I erase this here? So now we have service in reverse order of arrival, LIFO. Except that previously we looked at LIFO, MG1 LIFO preemptive resume. And in that case, we assumed that when a customer arrived, the customer immediately entered service and preempts anybody who was already there, if any. Now, we don't assume that. Now we assume that when the customer arrives, if the server is occupied, then the customer joins the queue, but is at the head of the queue. So now the system looks like this. There's the server, and let's say that there's somebody in it, and there's the queue. And now when the test customer arrives, instead of bumping the guy in the server, the test customer would squeeze right in there. Okay, so we want to calculate the waiting time distribution function for that case. Because we know that the mean has to be the same in every case, because as long as the next guy selected for service has a typical distribution, there's no bias, then we know that the mean waiting times are insensitive to the queue discipline. So we're going to get a different distribution for LIFO than we got for FIFO, but the mean should be the same. Okay, now here's the argument. It says, let TC be the arrival epoch of an arbitrary customer who arrives when the server is busy, and let T1 be the first subsequent service completion epoch. Okay, so the server is busy, so there's the service time, and the customer that we're talking about, the test customer right here, if he arrives when the server is busy, then he arrives during a service time. Same old argument. All of these have this renewal theory argument in them. And let the time at which he arrives, let's call that TC, and the time at which the first service completion occurs after that, that is the end of that interval, we'll call that T1. And the question is to let, first it says, let P hat J of X. Let this be the probability that J customers arrive in here, and that this interval is less than or equal to X. In other words, again, like what we saw before, we're going to have a joint distribution of the number of arrivals during this partial service time and the length of that partial service time. So this is the probability that between the arrival time of the test customer and the end of the service time that he interrupts, exactly J customers arrive, and the length of that interrupted service time, the remainder of that, is less than or equal to X. Okay, so what's that going to be? Well, first of all, we need the length of that. But of course, that's a forward recurrence time. So let's just call that H tilde. That's the distribution function of the forward recurrence time. So dH tilde of t is the probability that that interval lasts exactly t. And then lambda t to the j over j factorial e to the minus lambda t is the probability that exactly j customers arrive during that interval. And then I have to add that up. That is, I have to look at this as the value t varies from 0 to x, because we want this interval to be less than or equal to x. So this integral runs from 0 to x. Where, okay, so that's the answer, except of course that h tilde of t is equal to 1 over tau times the integral from 0 to t of 1 minus h of u du. This is the renewal theory result, where h is the distribution function of service times. Okay, so now what's w of t, the distribution function of the waiting time for mg1 LIFO? Well, the probability that the customer waits less than t is equal to the probability that he waits less than t given that he finds a server idle times the probability he finds a server idle plus the probability he waits less than t given that he does not find it idle times the probability that he does not find it idle. Well, the probability that he finds a server idle is 1 minus rho, and the probability he waits less than t, if that, is 1. The probability that he finds a server busy is rho. Now, if he finds a server busy, then what's the probability that he waits less than t? Well, okay, what must happen? First of all, here is the probability that when he arrives, he finds t minus less than or equal to t minus x remaining in the interrupted service time, and j customers arrive after him. Remember, we only care about the customers who arrive after him because this is LIFO service. Now, if exactly j customers arrive after him, then the length of time that is going to continue is going to be the j busy period. Okay, because what happens is, okay, here's our customer, he arrives here, and during this service time, exactly j new customers arrive. Now, those customers are now in front of him. He is not going to enter service until each of these customers is served, plus any customers who arrive later than that. Okay, so how much time does he wait because of this customer? He has to wait a 1 busy period because he waits for this customer's service time and all of his descendants. Likewise, he has to wait a 1 busy period for this guy and so forth. So the length of time he has to wait is the sum of those j1 busy periods, which is a j busy period. So if bj is the distribution function of a j busy period, which of course we know in principle, then dbj of x is the probability that those j busy periods last exactly x. Okay, now I have to integrate that as x runs from 0 to t, because we want his total waiting time to be less than t, and I have to sum this as j runs from 0 to infinity. Okay, so let me argue that one again. What's the probability that in MG1 LIFO, the test customer waits less than t? Well, he waits less than t if he finds a server idle. If he doesn't find the server idle, which occurs with probability rho, then the probability that he waits less than t is given by this. Okay, now why is that? Okay, well, when he arrives, if he doesn't find the server idle, he interrupts the service time. If he interrupts the service time, then between his arrival time and the end of that service time, other customers will arrive. This is the probability that during that interval, exactly j other customers arrive, and that time is less than or equal to t minus x. Now, if he is to wait less than t, then the total additional time caused by these j arrivals who are going to be served in front of him, that must be less than x, because that must be, yeah. If the total length of time of the additional customers, of whom there are j, is exactly x, then the total time that he waits will be less than or equal to t. I think I said that right. Okay, so let me say that again. I mean, I got it in my head, but I've got to say it so it makes sense in English. Okay, when the test customer arrives, this is the probability that j additional customers arrive in the remaining service time that he interrupts. And this is the probability that the remaining, that is this jointly, is the probability of that, and that that remaining time is less than or equal to t minus x. Now, when he arrives, the length of time he's going to wait is going to be the length of time that remains in the service time that he interrupted, plus the length of time caused by the arrivals that have occurred during that time. Now, during that time, each of those arrivals will be served, plus any other arrivals that occur, because this guy doesn't enter service until the system is otherwise empty. It's last come, first served. So what that means is that he has to wait until this guy and his busy period finishes. But then he has to wait until this guy and his busy period finishes, and so forth. So that each of the j customers, or all of the j customers in total that arrive during this time, will generate an additional length of time that our test customer has to wait, and that length of time will be exactly a j busy period. So this is the probability that that j busy period is exactly x. This is the probability that in fact it is a j busy period, and the additional remaining time in the interrupted interval is less than or equal to t minus x. This adds up as x runs from 0 to t, and this adds up over all possible values of j. So therefore, this is the probability that if he in fact is blocked, if he interrupts a service time, that his additional time from that instant until he enters service is less than or equal to t, and that's what we need. Okay, so this may or may not be helpful. It's explicit because we know this, that's given by this, or that's given by that, and we know this. Okay, now the rest is arithmetic, because now you can take transforms here. I'll write it over here. And if you do that, you get the following result. By a lot of arithmetic, because we have all these integrals, but remember, we know what they all are explicitly, we can find that omega of s is equal to 1 minus rho plus, the statement in the book, this is equation number 2 in that exercise. And of course, it's all worked out in the solutions manual. 1 minus eta of s plus lambda minus lambda beta of s divided by s plus lambda times 1 minus beta of s. Now, amazingly, this piece right over here we know is the same thing as beta of s, because our earlier result said that the Laplace-Dirichlet transform of the busy period was equal to the transform of the service time evaluated at s plus lambda minus lambda beta of s. So I can replace that by this, and that simplifies my expression. Okay, now you can do two things with this. One is you can differentiate this, and you can get the moments. And in particular, if you differentiate it once and set s equal to 0, you'll get the Palachek-Khinchin formula. At least you better. I haven't done it, but it must be true. At least I haven't done it recently. Okay, so assuming that that works, then that's another argument. That's a verification or evidence supporting the contention that the average waiting time does not depend on the Q discipline as long as it's a non-biased Q discipline, and is the same as you get for FIFO service. You can also calculate the other moments, so you can see the variability. For example, it turns out, I think obviously, that LIFO service is more variable than FIFO service, which means that even though on the average they're the same, a larger number of people are going to get very short waiting times, and a larger number of people are going to get very large waiting times. Finally, I can actually invert this using the same kind of arguments as before, and let me just write down what the answer is. It turns out that explicitly the distribution function, and you can verify by transforming this, is equal to 1 minus rho plus lambda summation j equals 1 to infinity e to the minus lambda t to the j minus 1 over j minus 1 factorial integral from 0 to t of 1 minus h star x dx. And now you can see that once again, you get terms in there that look sort of familiar. I mean, this is a Poisson term right here. And this is like a forward recurrence time. I could make it into that by dividing. And this is a forward recurrence time of a sum of j service times. So that indicates that there's probably an argument by which you could get this, and you can see that all of these things are somehow connected. They all have similar pieces in them. So that the indication there is that there's probably an argument by which you could get this other than the one that I just went through, which is to say, well, I'll simply take the transform of that, get that, and then invert that transform. So if you like to do arithmetic, if you like to take transforms and integrate and all that kind of stuff, classical applied mathematics kind of stuff, well, there's a lot of things to do here. And if you like to see, which is what I like, to see how all of these things fit together and try and understand what why they fit the way they do and what the relationships are, and try and come up with arguments that avoid all of mathematics, then this is fun, neat stuff. Okay, any questions about this? Everybody still awake here after multiple hours of this? The only reason I'm awake is because I'm actually standing here, but if I stopped talking, I'd probably zone out. But no, I wouldn't, because this is so exciting, this is so interesting, that even if you were had been deprived of sleep to the point of hallucinations, this would keep you awake. Maybe this is a hallucination itself. Okay, so if everybody's up to date on that, let me go to the next topic, which is the MG1Q with finite waiting room. I'm not going to be able to finish that, I think, but I'll get it started. Maybe I can finish it, but I won't rush. Okay, so here's what we're looking at. This is a very important problem from a practical point of view. And it's very tricky. Now in the book, this is called MG1 with finite waiting room. And I think it's said that the waiting room is of size n. In other words, there are n waiting positions. So that means that the system looks like this. let's say that here's the server, and now we have a bunch of waiting positions. And in that notation, there are n waiting positions. So the capacity of the system is n plus 1. What happens is that when customers arrive, and if they find all the waiting positions occupied, then they're lost. So what you want to calculate here is you want to calculate pi sub n plus 1. Because that's the fraction of arriving customers that will be denied service because there's not enough buffer space. Now, the standard notation that people use nowadays, which was less so at the time the book was written, which was now 15 years, believe it or not. Well, you believe it, but I don't believe it, because it doesn't seem like 15 years. Anyhow, the book was published in '81. Now, people call this MGK, or MG1K, typically. And the K here represents the total capacity. So if you see this, what this means is that you've got an MG1Q with a finite number of waiting positions. The total capacity is K, which means that there are K minus 1 waiting positions. OK, so I'm going to use this notation because that's what's in the book. But the title of it might very well be the MG1KQ. And we're going to take n plus 1 as the value K. OK, so K equals n plus 1 here. That's the total capacity. Now, what's the difficulty with this? The difficulty with this is, how do you calculate pi n plus 1? Well, one way is you could look at it just like ordinary MG1 and calculate those probabilities from the viewpoint of the arrival, except that you would truncate. Instead of having an infinite number of equations, you would have a finite number of equations, because you couldn't have a state higher than n plus 1. Well, that's actually even more difficult than the case where you have an infinite number of waiting positions. Because if it's finite, then these generating functions have boundaries, and things don't work out very neatly. So in principle, you would think, well, somehow or other, I ought to be able to write the equations just as I did before, but now there's only going to be a finite number of them. Now I should be able to solve them, but the solution is going to be much more difficult because there's a finite number of equations, and therefore there's a boundary condition. From a mathematical point of view, in theory, it should be easier because there's no question about existence and uniqueness and all that stuff that you run into with infinite sets of equations. But in terms of the manipulations, it's going to be harder. So the obvious way to do it is to look at it from the viewpoint of departures. But now that gives you this problem. What is the probability that a departing customer leaves the system in state n plus 1? Well, if you're talking about a customer who departs after completing service, it's 0. Because if I have a system with n waiting positions, then if all the waiting positions are filled, then when a customer leaves, the number that customer leaves behind him is n, not n plus 1. So we have the strange fact that the probability that the arriving customer finds state n plus 1 is generally positive. A customer can find all the waiting positions occupied, but he can't leave all the waiting positions occupied, at least after being served. He can only leave the system with all waiting positions occupied if he leaves immediately. So now we have the strange situation where the pi n plus 1 does not equal the pi n plus 1 star, even though we have a theorem that says that it does. Well, actually, we don't, because the conditions of the theorem are not met. Because if you draw a picture of this, it looks like this. Let's say that an arrival occurs, and you jump up by 1, and then you stay there a while, and maybe another arrival occurs, and so forth. Now, let's say, for the sake of argument, that this is level n plus 1. So we bop around here like this. If an arrival occurs when the system is in state n plus 1, that's a lost customer. I want to consider that customer because, after all, that's the probability I want to calculate. I want to calculate the fraction of customers who, when they arrive, find the system in this state and are therefore lost customers. However, from the viewpoint of this theorem, if I want to count these customers, I have to recognize that the system either doesn't recognize those customers because it doesn't jump when one of those customers arrives, or if I want to take the viewpoint that this arriving customer is also a departing customer who leaves the system in state n plus 1, I could do that. But then I don't have a one-step system, because then I have a system which jumps up and down at the same instant in time. So I can't apply the theorem that said that that in general pi j and pi j star were equal. I can't do that anymore. Okay, because that assumes that all the jumps occur one step at a time. And in this case, if we count these customers, then I am simultaneously having a jump up and a jump down at the same time. So I have to deal with that question. Okay, now, nevertheless, we could still write equations for pi j star for j equals 0, 1, 2, up to n, because I can still leave behind n customers. Okay? So, in fact, I could do this. If you look at ordinary MG1, remember what the equations were for ordinary MG1. We said the probability that a departing customer left behind j is equal to the probability that the previous customer, previous departure, left behind 0, and during the ensuing service time, exactly j new customers arrived, plus the probability that the previous departing customer left behind I, times the probability that during that customer service time, exactly j minus I plus 1 new customers arrived, summed over all I from 1 to j plus 1. So this was for ordinary MG1. Okay, now, what about our case where we have a finite number of waiting positions? Now I claim you can still find the probabilities for j running from 0 to n. In fact, you can find them recursively, because all I got to do is, let me do it over here and write those state equations out. What I have is pi j star is equal to pi 0 star pj plus the sum as I runs from 1 up to, let's see, yeah, up to j of pi I star p j minus I plus 1 plus pi j plus 1 star p 0. So all I did was go over to this equation and separate out the last term. And then you see that what that means is that I have an equation which for each j gives me the pi star in terms of all the previous ones. So in other words, if I wrote these equations out, I could calculate pi 1 star in terms of pi 0 star, and pi 2 in terms of pi 1 and pi 0 star, and so forth. So the end result is that I can solve all these equations. That is, I can write pi j plus 1 star is equal to 1 over p0 times all of this stuff, right? I just bring this on this side, divide by P0, and I got it. And that's going to be valid for j equals 0, 1, and so forth up to, now the highest value j can be would be n. Would be n minus 1. So when j is equal to n minus 1, that's pi n star. Okay, so the conclusion at this moment is that the pi stars are known. In other words, numerically, I can calculate them. In fact, the way I would do that is I would assume that pi 0 star has some arbitrary value like 1. And then I would calculate pi 1 star, and then pi 2 star, and so forth. I calculate all of them, then I divide each of them by their sum, and that would normalize. And so now what we're assuming is that what's known is pi 0 star, pi 1 star, and so forth up to pi n star, and that the sum of these pi j stars as j runs from 0 to n is 1. Okay, this is equation 9.1 in the textbook right here. Okay, now the question is, okay, that's 9.1. This is 9.2. Now the question is, how can I calculate the distribution? Okay, so we know pi 0 star, pi 1 star, pi n star. We know those guys. We want to find pi 0, pi 1, pi n plus 1. How do we get these guys knowing those guys? Okay, to answer that question, we go back to this diagram. Here's the claim. See if this makes sense. Pi j star. What is that? Well, let's look at this diagram, and let's ignore these transitions, or these arrivals that don't cause transitions. So let's look at the diagram without those guys. And if you look at the diagram without those guys, then it's true that the pi j's and the pi j stars have to be equal. Except that we're not counting in the arrivals that find all the awaiting positions occupied. So what I claim is that pi j star is equal to the probability that the number present is j, given that the number present is less than or equal to n, because I'm discounting these guys right here. Okay? In other words, I'm going to argue that the pi j stars conditioned are the same as the pi j's, except that the pi j's, these are the pi j's here, except that they're based on the condition that we are not looking at the arrivals that occur when the system is in state n. Okay, so I think I'm not clear on this. Okay, let me go back over this. We know we can calculate these pi j stars because we can get them here. Okay, now I look at this diagram and I say, okay, now I'm just going to look at the ups and downs on the diagram, and I'm not worried about what's going to happen here. So I'm not allowing, I could imagine that those states occur, but I'm not going to allow any state which is greater than or equal to n. Okay, so as long as I don't count those guys, I can say that the probability that a departure leaves behind j is the same as the probability that an arrival finds j, given the condition that I'm looking only at those states that are arrivals that occur when the system is less than or equal to state n. Now, I think actually, I think I made a mistake here. I think I really mean n plus 1 here. In my notes, I have that as an n, but that doesn't seem to make sense to me now, because n plus 1 is the capacity of the system, n is the number of waiting positions. Okay, so I want to ignore the guys that arrive when the system's capacity is full. Okay, does that make sense? If I ignore these guys, then the probability that a departure leaves behind j is the same as the probability that an arrival finds j by the old theorem, except that we're conditioning on the fact that we're looking only at arrivals that occur when the system is not in its completely blocking state. Okay, now I rewrite this as the probability that n equals j and n is less than or equal to n plus 1 divided by the probability that n is less than or equal to n plus 1. But since this is the maximum value that capital N can be, the joint probability that the number that he finds is j and is less than or equal to n plus 1 is equal to the probability that the number that he finds is j. The denominator is a constant. Let me leave it as at the moment for the probability that the number he finds is less than or equal to n plus 1. Okay, now I notice the denominator is a constant. We don't know what it is, but it doesn't depend on j. And the numerator is simply pi j. So my conclusion is that pi j is equal to c times pi j star for j equals 0, 1, up to n. Okay, so now I can, since I know what the pi j stars are, I now know that the pi j's are proportional to the pi j stars. What I have to find is what that proportionality constant is. So I've got two things going. One thing is that I know that these probabilities must sum to 1, so I can get that through normalization. The other is I've got to connect somehow the pi sub n plus 1. So what I'm going to do, and I'll do that next time because I've only got a minute left, is I'm going to find through normalization and through the fact that the relationship between offered and carried loads, I'm going to get a separate equation for pi n plus 1. And then putting these things together, I will be able to get a solution. Now, just let me stress that from a practical point of view, this is a very important problem. Because in real life, what you're typically doing, say, in a telecommunication system, is you want to provide a certain number of buffers, and the way you determine those buffers is to provide the number of buffers large enough such that the fraction of customers who are lost is less than or equal to some number, like, I don't know, 10 to the minus 6 or something like that. So typically what you do is you find out how to calculate this pi sub n plus 1, and then you find out what it must be, the largest value it can be, smallest value actually, it can be, such that this condition is met. Now, if this probability is relatively small, as it is in these kinds of applications, then you could say for all practical purposes, the number of buffers is infinite because you're only going to lose one call in a million, say. So you determine the value of n, but then after that, you treat the system as an ordinary MG1 system in terms of calculating waiting times and all the rest of it. So the trick here, the important thing is to be able to calculate the probability pi sub n plus 1 so that you can determine the value of n that the number of buffers that you're going to put in when you design such a system. Okay, so next time, what I'm going to do is I'm going to repeat this piece right here to make sure I got this thing right or correct it if I didn't. And then starting then from the fact that we know that these probabilities are proportional, determine the extra equation required to calculate this, put it all together, and get the formula that then gives me this answer. Okay, any questions or anything before we quit? Okay, so I'll see you tomorrow, I hope.